very much. So, yeah, good morning, guten Tag, verehrte Gäste, distinguished guests, colleagues, dear colleagues, liebe Kollegen, liebe Kolleginnen, in Halifax and in Berlin. It's quite exciting, actually, this thing. Many thanks to the German-Canadian Concourse for putting this pretty amazing event, and I'd say technological tour de force, together. It really brings great personal satisfaction to me to be involved in this event, because this event recognizes the importance and the need for information about our oceans. It recognizes implicitly the importance of international cooperation in obtaining and using that information. And of course, it recognizes the value of Canada-Germany cooperation on that task, and I think also recognizes the fact that in many ways Canada and Germany are leading the way in this what is a global effort. So my talk's going to focus on one specific, fairly focused aspect of the ocean as an example of the need for data analytics about our ocean and the need for international cooperation. And I warn you, bits are going to be a little bit intense, and I'm going to go over some of it quite fast, and you might be tired at the end of it. But anyway, but in my talk, I'll try and give, throughout my talk, which will focus on the ocean carbon sink and how we attempt to measure it, I'll also try and give intermittently examples of the increasing amounts of data that are involved in this task, and therefore the increasing need for sophisticated data analytics to get a grip on this particular problem, which is just an example of many other similar problems involving the ocean. So I'll start with this as the context. This, of course, as you know, in December last year, almost 200 countries signed on to a major commitment to finally do something about the problem of climate change. Now, leaving aside recent events, this is a major commitment, and it was a major step forward. I just want to point out, though, that there are many things were agreed to, but especially important was Article 4, which agreed that countries would strive to reach a global peaking of greenhouse gas emissions as soon as possible, and to undertake rapid reductions thereafter in accordance with the best available science, so as to achieve a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of this century. It's not very far away. Article 14 further said you've got to figure out how good a job you're doing on this. And so Article 14, the countries agreed to periodically take stock of the implementation of this agreement to assess the collective progress towards achieving the purpose. So there's a goal, and a pretty demanding one, in terms to balance sources and sinks, and there's a process put in place to assess how well we're doing. So part of that is the ocean carbon sink, a very large part of it. So this diagram here says, you know, first of all, or this slide attempts to focus on what are the sources and sinks that we're attempting to balance on a global scale. And it's expressed as a budget for anthropogenic carbon, the carbon mobilized as a result of direct human activities. And the balance is between fossil fuel emissions, and emissions from cement production, which we've got a very good handle on from knowledge of, from economic data, basically. The atmosphere is the biggest sink, if we look at it that way, for those emissions. The ocean is an important sink, and it's been characterized as a result of measurements and models, which I'll talk about more in a moment. And we have two important arrows on the land. One is a land use change term, which reflects primarily the impacts of deforestation and changes in the use of the land surface as a result of human activity. And then, to balance the budget, and that's why it's there is a sink on land, which is actually calculated from the mass balance of the other terms. So the land sink is not independently estimated. It's calculated from the mass balance of the other terms. And that means that the land sink term depends on, for example, our estimates of the land use change term. If that goes up, the land sink has to grow. Has to, because it's a mass balance. Similarly, if the ocean sink was underestimated or overestimated,
that would have implications for the value of the land sink shown in that budget. So when you look at these terms in the budget, we have excellent measurements of the atmospheric sink, we can call it, thanks to people like Charles David Keeling and the famous Keeling curve. This is well known. The ocean sink is our next best known term. We actually can measure it, but it's not easy. It's definitely not easy, and I'm going to make the case we're not actually putting enough effort into that right now, given the agreement we've just entered into in December. So, what is the ocean carbon sink? The ocean carbon sink is global. Basically on the top right-hand panel there, it shows how the ocean carbon sink has changed over time in terms of the amount of carbon taken up by the ocean per year. It's the rate of uptake, if you like, of the emissions driven by mankind. And you can see the red line is the ocean uptake, and the black line is the changing concentration of CO2 in the atmosphere. And they track each other very, very well, because that's the driving force for the ocean to take up more carbon, is the fact that the atmosphere is increasing. Now, we measured the cumulative uptake once in the ocean, and that was done during the 1990s. And the top left panel shows a large number of cruises which were done on research vessels throughout the world oceans. Each one of those red lines is a research expedition crossing an ocean basin, making a whole bunch of measurements from the top of the ocean to the bottom. And these were made over an 8-year period by the international community all over the world. And in the process of that, we measured CO2. And the lower left panel shows the distribution, and what we estimate from those observations, the distribution of the extra CO2 contained in the ocean at that time relative to how much we believe was in the ocean 200 years earlier, before the Industrial Revolution. And if you look at that map, you can see that the distribution, whereas in the atmosphere the distribution of the excess CO2 is uniform because the atmosphere is well mixed, the ocean's very non-uniform in terms of where that is. And you notice the big red blob right off the shore of eastern Canada, right in the Labrador Sea and the Northwest Atlantic. That's where the most intense storage of these excess CO2 from burning of fossil fuels is located, right on the shores of eastern Canada. And so in the bottom right panel, we see how that cumulative sink is estimated to have increased over time. The red line is from models. There's one data point with the arrow, which was the data point collected in 1990s. And then there's some additional data points on the diagram, but they're not actually independent data points. They're just model-based extrapolations of the 1990s data point. So we've measured it once, and we've extrapolated it for 20 years. And that initial measurement was involved for carbon measurements alone, it required other types of measurements as well, about 350,000 measurements made over the world ocean, each one involving chemical analyses. So what the ocean carbon sink is an ecosystem service. Basically, that CO2 taken up by the ocean and stored there is not impacting climate change. Maybe doing other things in the ocean, but it's not impacting climate change. It's reducing the impact of CO2 on warming and other climate change impacts. So as a result of the movement towards establishing carbon pricing in different countries, including in Canada, most recently proposed, we can put a value on this ecosystem service that the ocean provides. And that's done in this slide here, where we estimate the current size of the ocean carbon sink in the last decade and multiply it by the price, projected carbon price proposed by our federal government in the next decade. And we work out that this global ocean sink value is worth on the order of half $500 billion per year. It's a lot. And if we take just the Northwest Atlantic part, the part off eastern Canada, which is roughly 8 to 10% of the global sink, it's the most intense sink, then that part alone is worth, as an ecosystem service, with that level of carbon pricing, $50 billion per year. It's a significant service that the ocean provides to the planet. And if the ocean sink were to weaken or to change, if it was to weaken, and I think all indications it will likely weaken rather than strengthen, then in order to meet the goals set by COP21 of carbon greenhouse gas neutrality between sources and sinks, then we'll have to do something about it. We'll have to know, first of all, and we'd probably have to do something about it. And one possible thing we might have to do is change the carbon price to accelerate the reduction of emissions. So, the Northwest Atlantic. Why the Northwest Atlantic is so important? Well, it relates to special processes operating on our shores, and most of us who live in Atlantic Canada know what some of those processes are. This ocean off our coast here is one of the most dynamic parts of the world ocean. On the left-hand diagram is a model run by colleagues in Guillemar, just showing the surface circulation of the Atlantic Ocean, and you can see how dynamic the surface circulation in the Northwest Atlantic is compared to pretty much anywhere else. You see especially the Gulf Stream, that's the red, and moving northeast, and you see the Labrador Current carrying ice periodically out of the Arctic. And in the process of that, especially the Gulf Stream moving north, then the waters are cooling, and that causes the waters to naturally take up CO2 from the atmosphere. And we can look at that in a global scale by the lower right map, which shows the distribution of the flux, or the transfer of CO2 between the atmosphere and the ocean on a global scale each year. And the North Atlantic is shown with very blue colors. It shows it's a sink for CO2. And that's because the waters are cooling, and as they cool, they're taking up CO2 from the atmosphere. And other regions are sources, natural sources, where CO2 is being emitted. And what we've done in the last 200 years is we've slightly increased the sinks and slightly decreased the source regions, such that the overall transfer of carbon is in. How do we know this? Well, we know it from collecting data from the surface of the ocean, and very often these data are collected on ships of opportunity, which I'll talk about in a minute. But the other reason the Northwest Atlantic is a big sink is because there's a lot of wind. We know that. And that accelerates the transfer of carbon between the atmosphere and the ocean through gas exchange. Okay, but the main reason why the Northwest Atlantic is such an important sink for CO2, for anthropogenic CO2, is because the carbon doesn't just stay in the surface of the ocean, it's transported into the ocean interior. And that takes place by a process which we commonly refer to as deep sinking of surface waters in winter. They become cold, and they become dense, and in just a very few locations of the sea surface globally, those waters become dense enough to sink down into the ocean interior, where they can carry CO2 and oxygen from the sea surface into the ocean interior as those waters sink. And that happens especially in the Labrador Sea. And it's shown here by some data that a colleague of mine in Kiel and myself made many years ago now, in 2005 GCC, using the first deployments of oxygen sensors on ocean floats, kind of robots that go up and down in the ocean and can measure oxygen as other properties on the way. And you can see as you go from summer into winter, the oxygen concentration deepens, that's the greens, as the concentration increases, and the oxygen penetrates into the ocean interior as the waters sink into the ocean interior, until late winter when that process stops. And in that particular winter, the first one, you can see that that penetration of the high oxygen into the ocean interior reached about 1,200 meters, and then stopped, and then the oxygen goes away again. It goes away because the ocean circulation takes the oxygen away, just like when we breathe in, the oxygen we breathe in is transported to our fingers and toes by our bloodstream. So some amazing work done at Bedford Institute of Oceanography just across the water here by Igor Yashayev and John Loder and others has taken results from those types of floats made over the last almost 20 years and looked at how this breathing has changed from year to year in the Labrador Sea. And it's highly irregular. You can see that those kind of dotted lines in each year show the maximum depth to which these surface waters sink in each of the individual winters. And it changes a lot. You can see the 2005 winter, about 1,200 meters, as I said. But for some years, it only reached like 400 or 500 meters. A lot of variability. So the breathing's irregular. And in the last couple of winters, it's been especially deep again. So there's a lot of variation here, and this is being monitored by floats, but also by cruises operated by Bedford Institute of Oceanography that transit this region every year. We can measure carbon on those cruises and see how the carbon changes. We can put some of these data together, and especially the data from volunteer observing ships, and construct maps using data analytics. This is using self-organizing maps and advanced neural network techniques to extrapolate our limited data collected where we can in this case, the whole Atlantic Ocean scale. And this map here from a recent paper shows the flux change of CO2 between the atmosphere and the ocean over a decadal, a 10-year time period. And you can see that some parts of the Atlantic, the sink has increased, those are the blue areas, and some, the sink has decreased, and those are the red areas. And you can see the Labrador Sea especially has increased, the sink has increased over that 10-year period. This may just be natural variability, or it may be longer-term climate change, we can't say. What I want to point out at is the data we have for making these statements about the sources and sinks and how they're changing over time are they're growing, but they're still limited. Here you can see the distribution of the data which go into that nice first picture on the left-hand side. And you'll see, remarkably, we have no data from the Labrador Sea, even though with the wonders of data analytics, we can extrapolate, and I think reasonably well, into regions where we have no data. We actually have no data with which to verify this, no data over an annual cycle. So all of these observations you're seeing here were collected, most of them anyway, were collected from commercial vessels, which were measuring CO2 in the atmosphere and the surface ocean. And at the moment, just for the Atlantic Ocean alone, as of 2013, this map here represents probably now about 5 million individual CO2 data points. You start to see the increase in the data, but it's still not enough. This is the types of vessels we use. On the left-hand side is the Atlantic Cartier, which is a ship many of us will recognize entering Halifax and heading into Fairview Cove regularly. Guiomar in Kiel and us here in Dalhousie cooperate on maintaining measurement systems on that vessel. It's actually almost operated by Atlantic Container Lines. And the lower left panel, you start to see the coverage which has been collected from this particular crossing, not always this particular ship, over the last 10 years or so. We're getting a lot of data year-round with this type of approach. The systems we have installed in the ship right now look very much like lab equipment, and you know, not every ship's engineer is so excited about having this in their engine room. And so we've been working at Dalhousie very much with companies like Atlantic Towing and others to work on developing more robust systems which can get approval by the certification agencies and so on for installation on pretty much any commercial vessel without freaking out the ship's engineer. So we're working on that one specifically with the Atlantic Condor, which again, many of you will have seen here in Halifax Harbour as it heads out and back across the continental shelf to Deep Panuke. So this line, this one crossing of the Atlantic, since 2004, when Guiomar started these measurements, has collected more than 350,000 CO2 data points, and there's other vessels equipped in similar ways to collect the data. I'm going to skip over this one fast because it's very complicated. But it's not just the exchange at the surface, it's also the transport away. I mentioned the kind of bloodstream idea. And we can monitor this sort of flow of heat and fresh water, but also potentially of carbon and oxygen by making measurements, fixed measurements with oceanographic moorings at certain locations where you're measuring the current flows in the deep ocean and also measuring the properties which are being transported. And an international program called OSNAP is attempting to measure the physical transport right now. These moorings are out in the water right now, including a set of oceanographic moorings off the coast of Newfoundland at 53 degrees north, which represents a German-Canadian cooperation between the Bedford Institute and Guiomar in this particular case. And we at Dalhousie have just recently supplemented that by putting oxygen sensors on those same moorings so we can start to monitor the flow in and out of oxygen at depth from the Labrador Sea, those sort of blue currents shown in the top left here. So this is going on, and I also want to point out further to the northeast there in the center of the Labrador Sea, where the little German-Canadian flag is, a central mooring located in the center of the Labrador Sea, which has been maintained by Guiomar in Kiel in Germany for decades, and which we've recently added to from Canada by installing something called the Sea Cycler. Now this is new Canadian technology developed initially by engineers at Bedford Institute of Oceanography. Actually, it's been a long development path, and which we've recently at Dalhousie worked to kind of bring to the next level. It's an underwater winch, which is presently out in the center of the Labrador Sea right now. It's been out there since May, collecting data on CO2 and oxygen and temperature and salinity, profiling a set of up to 13 sensors from a depth of about 150 meters to the surface usually every 20 hours or so. Sometimes more frequent, sometimes less. We can change that. And this is out in the Labrador Sea right now, and there's also a glider, kind of another type of underwater robot run by Memorial University out there right now, transiting between the long-term mooring of Guiomar and our new sea cycler mooring in the Labrador Sea. And so this is just an example of international cooperation to get this, the thing in the water. It's a big piece of equipment, so we, our crew went on the Maria S. Merian, the German research vessel, in May of this year. Prior to that, in a previous visit last year, many of you may have been involved in the Open Ship when 1,000 visitors from Halifax visited the Marianne when she was docked near the seaport market here, and gave an opportunity to look at the most modern seagoing infrastructure, including our sea cycler. But in May, we actually deployed it successfully from the Marianne and put it over the side in remarkably calm conditions, which was nice. And this is the team of German and Canadian scientists who did that, led by Chief Scientist Johannes Carstensen from Kiel. So the data are just coming in. We get the data pretty much every day when it's not too rough. We get the data telemetered by satellite to our lab. And we're just collecting, I mean, the data are completely unique. There's nothing ever been collected like this before. And we're just now overloaded, frankly, suddenly by a large amount of data, which have to be analyzed and interpreted. So it's very exciting what we can start to see. I'm not going to go into details about what we see, but just to point out that now, since May, when the Sea Cycler is deployed, we've got 12 million raw data points have been transmitted to us. And we see this type of technology deployed with other types of underwater robot technology and surface robot technology as being part of some coordinated package of the multi-platform autonomous observing networks that ultimately we should put out in the Labrador Sea in order to monitor the carbon sink and the role of this region in climate for longer periods. Now, data are one thing, but you never have enough data. You also have to combine data with models in order to make sense of the whole picture. And that has to be done, I think, with very sophisticated data analytics. It's beyond my experience how to do that, but just to point out that at the same time here in Canada, but also in Germany, we have excellent models of this region, including to higher and higher resolution. Here, 1/12th degree resolution models of these types of processes, but potentially going to much higher resolution. These models generate, for each model year, each simulation of a year of maybe the carbon uptake, generate multiple gigabytes, basically terabytes of model output, which have to be combined with our observations in some sophisticated way to tell us exactly how the system, if we can, how the system's functioning. So within the Ocean Frontier Institute, we have a chance to approach the scale of effort required to tackle this sort of problem. And specifically within the Ocean Frontier Institute, which has been mentioned already by, we have a one module of that will focus on this Northwest Atlantic carbon sink and develop what we seek to do by combining the expertise within Canada around national labs like BIO, but also people at Memorial, but also people in Germany, develop an advanced toolkit linking advanced observing systems, high-resolution models, and data analytics in order to allow us to do an audit of this region's carbon sink every 5 years. We need to demonstrate the approach. We have to work out the approach, how we do it, demonstrate that we can do it, and then this approach becomes a way to provide a regional validation point with an uncertainty estimate, which can be used for the assessment exercise that COP21 said has to be put in place. And currently, I think this is the only realistic way of doing it regionally, rather than attempting to do a 10-year survey. Well, the one survey we did in the 1990s took us 10 years. We can't do it every 5 years. So we can focus on regions. So that's the Ocean Frontier Institute. Gives us the scale of expertise and also infrastructure and people that allows us to envision doing this sort of thing. This is the Ocean Frontier Institute showing the international partners. Of course, very important partners are federal partners, DFO, Environment Canada, and Climate Change, and Department of National Defense. But the international partners are really impressive. Some very famous ones there. That was quite deliberate on our part. But of course, building strongly on our existing collaborations with Germany, especially with the Helmholtz Institutes, in this case, in the Alfred Wegener Institute in Bremerhaven, and the Guillemot Institute in Kiel. So, how did this come about? Well, as many of you may remember, or some of you remember, Frau Merkel did visit Dalhousie in 2012 after a kind of side trip to visit Prime Minister Harper. She really came, I'm sure, to visit Dalhousie. And at that point, you know, it was already clear to her, I think, that the oceans are both important and under pressure. And she's been a great supporter of marine science in Germany, of course. And after her visit, I think that impression was only accentuated, and she was quoted in the German press to say that afterwards, shortly after the visit, we could talk for hours and tell incredibly sad stories from the sea. It's in some cases dramatic what's happening there. And that's true, not all sad, but some of it is. And, but most importantly, with that visit, we were able to put in place, or put the signature on, the beginnings of an international structure required to tackle problems of this scale. This was this Canada, or Helmholtz agreement with the Helmholtz labs, 3 labs of the Helmholtz Society, one in Potsdam, one in Bremerhaven, and one in Kiel, to focus on change, risks, and resources in the oceans, especially with a focus on the transatlantic and the Arctic. And then out of that visit also came our TOST Host Graduate School, which Ambassador Vrendt visited recently when we had our summer school, including a really pretty amazing Dragon's Den competition where all the German Canadian students got together and proposed a whole bunch of interesting business propositions for ocean-related businesses. But this links Kiel and Halifax very tightly together in terms of student exchanges funded jointly on both sides of the Atlantic, and bringing students together for joint seminars and joint projects, again focused on the North Atlantic. So, we've got massive, massive challenges, which if we're serious about issues like climate change and balancing carbon sources and things, we have to deal with. It's pretty obvious when you think about the complexity and scale of the ocean that this can only really be tackled. It is only successfully tackled as a result of international cooperation. No one country, no matter how powerful, can sort of do it on their own. And yet, the fact remains that when you look at those institutions linked together by the Ocean Frontier Institute, each one of those is a national institution. And you have to go to fairly complex lengths to kind of link them together, to get them working together and moving in the same direction. I personally think that the Helmholtz Canada Memorandum of Understanding, the TOST Host Graduate School, and the work that we've been doing together between Germany and Canada in the Northwest Atlantic really show the way, and it's a way that will be accelerated by the Ocean Frontier Institute. But I also think that Canada and Germany can use that as a basis and actually go considerably further into the future in terms of integrating the ocean science capacities and visions of the two countries. So with that, I'm going to finish.
Thank you, Doug.
Alexander, can you hear us?
Yes, and I can also see you. Do you see us?
Yes, we can.
Nice wave, Doug. Nice wave. Okay. So now, before we continue with our next speakers, we have about 10 minutes for questions from the audience. Of course, I would have questions myself too, but I want to give the audience the time and space. Because of this transatlantic dive of our data, we have to be very sort of, take our time and make sure both sides see and hear us. So, Hannes, if you look at your audience in Halifax, do you see a first question or remark? I do the same here?
So we do have a question.
Okay, then we
yes,
first take
we
a
have
question.
a question here, yeah?
Yeah, you take the first, then it's Berlin.
Okay, the microphone is on, yes. Okay, so what we'll do, I'm going to come out into the audience and hand you the microphone, and if you could just state your name and your affiliation, that would be excellent. Thank you.
Is it on? Oh, okay. I'll look at him too. Hi, I'm Desiree Stockerman, Motion Sonics. I actually have a question for Doug, which he alluded in his presentation about what is the effect on the ocean itself of the sink. And actually the second question is, the sink right now seems to be natural. It's just happening. It's not man-made. Are we looking at a man-made sink as well?
Okay, so both good questions. So taking the second one first, is the sink is natural in a sense. Yes, it's natural, but the sink is only there because we've changed the atmosphere. So before, the assumption is, and I think it's a valid one, it's been more or less shown to be the case, before the Industrial Revolution, the ocean and the atmosphere were in some form of steady state. So what went in came out somewhere else. And what we've done since then, by pumping CO2 into the atmosphere, we've changed that. And so the ocean now dissolves extra CO2 that it didn't before, and that's in direct response to our emissions. So it's natural in a way in that the ocean is sort of doing it without our assistance, but it's not really natural in a way, because the only reason it's doing that is because we've filled up the atmosphere with more CO2 than before. So it's not a direct human intervention to drive the sink like it would be if you were planting trees, but the sink is a result of us putting CO2 into the atmosphere. So then in the process of answering that question, of course I've forgotten immediately the first one, which was? Oh yeah, effect. So I'm being a little bit disingenuous by saying that the value is $500 billion per year, because of course there is a cost to putting CO2 in the ocean, which is difficult to estimate. But that is ocean acidification. So as we put CO2, more and more CO2 into the ocean, we change the acidity of the ocean, and that has impacts on life. And certain life forms and not on others, and certain places and not elsewhere. And of course there's a great deal of concern about those impacts, and those costs must have a value as well. They've been estimated, and they're not insignificant. So that has to be really taken into account as well.
Thank you. We have now a question here in Berlin. If you could please stand up and say your affiliation.
Yes, I'm Justin Robichaud. I'm the Counselor for Science Technology at the Embassy of Canada. The questions for Professor Wallace is about, you're very concerned about measuring the sinks and the CO2s through these instruments. Could you give us examples of potentially other potential applications that can come out of your collections of data that you're doing at the moment?
Yeah, so I mean, if the goal is to measure the sink, that's one thing as part of the requirement to do the so-called global stocktake every 5 years. I think it is essential that because the ocean is sensitive to climate change itself, and therefore the process of CO2 uptake by the ocean is sensitive to climate change, especially in places like the Labrador Sea, we need to get a handle on that by measurement rather than just simply blindly extrapolating. But in the course of collecting those types of data for that particular purpose, of course you learn a great deal more about the ocean, and of course you also drive technological innovation. In order to do this, you have to develop new sensors, deploy them, and which can be used in other environments for other purposes. But specifically, for example, with our sea cycler profiler in the Labrador Sea, the first thing that we're getting out of this is, I think, the first really solid estimate of the magnitude of biological productivity over an annual cycle in this region. And that's been approached from about 4 or 5 different ways, so we'll have 4 different ways to actually estimate that. And that becomes useful in terms of understanding how good our models of biological productivity are, both in that region, but it's a test of how well those models might be elsewhere. And of course, those models are the basis for some of our ecosystem-based assessments of how much food we might take out of the ocean and things like that. So I think there's spin-offs in other areas when you're tackling that one big question about the CO2 uptake. You're developing new technologies, testing them, often many of them made by, I should say, by Canadian companies. Many of the sensors are made here in Halifax or in Nova Scotia. But also learning how the ocean works, which can be applied to other problems.
Thank you. Hannes, I have another question over here in Berlin. Gentlemen, could you, sir, could you come to me, please? And say who you are and your question.
My name is Günther Tau from the company TBS. We are dealing with big data, but in other areas. And what I'm missing a little bit is the aspect that in your new institute, there is no compartment, with artificial intelligence. So you're piling up your data in silos, and you don't have a tool yet what to do with these things. And it's always the case. It's not only in the ocean and the auxiliary fields and every science that we can find out. So what has to be a bait to change this? We cannot just doing research for the next 10 years. The timeline is very short, and there will be, it's the last 5 seasons have been the hottest seasons in the weather forecast for more than, 300, 400 years.
Thank you.
No, and I share the concern over the time it takes to get anything done. And, yes, ocean research and most global change research is just too slow, right? I mean, relative to the scale and the rate of change, and I fully agree with that. In terms of specifically how we're going to deal with these large amounts of data, yeah, it's not sufficient to collect the data and then 10 years later start to work on them, as we used to do. No question, we used to do it that way. So within the Ocean Frontier Institute, we have a module based on ocean data analytics, and actually we have 2 modules which will be focused on ocean data analytics, where we will be working closely with experts on big data and on advanced statistical techniques. And we hope, if we do it right, and it's early days, if we do it right, we'll develop the tools and apply the tools at the same time as we're collecting the data. And so, but that also means that obviously that capacity, certainly within Halifax or within the Ocean Frontier Institute, isn't on its own enough for this scale of problem. And I think we see the Ocean Frontier Institute with its partners becoming a hub for something new, which would involve other parties as well. So there's people in this room who could speak to that better than I can, but I think we're aware of the problem, and I'm certainly aware of the urgency, and it bothers me.
Thank you. Questions over in Halifax, Hannes?
Not as of yet. Yes, okay. We have a question.
There's maybe a follow-up.
Stan Matwin, I'm with the Big Data Analytics Institute at Dalhousie. I just wanted to ask you about that first equation you had at the very beginning. And it's strikingly simple, because it's linear and all the coefficients are 1. So how do we know that? Maybe there is something that's nonlinear, or at least is more important. One of these 4 on the right-hand side is more important than the other. I was wondering about that.
Well, certainly the equation is frighteningly simple for such a big problem. I mean, it does represent, in the end, a global mass balance for a particular year, or in that case, it was applied for a decade. So it represents an average mass balance for a decade of these different massive compartments. The change, how that mass balance changes from over time, that is subject to all sorts of, and how it changes within the 10-year period, all sorts of really horrendously complicated non-linearities, which are sort of smoothed over in bringing everything together to that big budget. I think some terms are amenable just to measurement, the atmosphere is, but some terms are highly variable, especially the land use terms, and involve all sorts of climate-related non-linearities, which are estimated by models.
Okay, thank you. We start preparing here for our next presentation by Mrs. Mordick. I have a question, Doug, before you leave the podium. Okay. Why do you think it is that the German-Canadian relations work especially well in the field of ocean research and technology? I mean, you had our chancellor over. Right now she's saying goodbye to her friend Obama just down the road from here. But why do you think it is? Is it just the German-Canadian relationship? Is it our binding ocean? I mean, you could do similar things with the UK, which you probably do, but what do you think it is?
I think, first of all, of course, you know, I'm sure everybody in Berlin agrees that the Germans just love Canada, right? I mean, they just... But I think more seriously, it's partly a result of the strong emphasis of German science funding on internationalization of science, I think, and the significant investments that Germany makes in mobility and in international cooperation, which I think is a real model for the rest of the world, including Canada, I have to say. So I think that's another aspect which makes it possible. There's no question that the strength of infrastructure, German scientific infrastructure, makes this sort of work possible, and something that, looking around the audience, we can definitely learn from a little bit, because without infrastructure we can't do this type of science. So that's another very good reason for Canada to cooperate with Germany for sure. But I think it really lies probably almost on a personal level, and of course long history of common scientific interest in this region, going back decades, especially, for example, between the Bedford Institute of Oceanography and an earlier generation of German scientists in Kiel and in Bremerhaven especially, but also on the geological side, also the common interests and exchanges. And these exchanges, and out of that friendships and partnerships, they just kind of build up over time to make it possible to do things together. And I think we're just at that point right now with ocean science to make the cooperation possible.
Thank you very much, and we will come back to that question of this specific area of German-Canadian relations in our panel at the end of the conference. Thank you very much, Doug. This applause is for you and your presentation. Thank you so much.